Hello again, everybody. So the other project I'm talking about today here is a reprise of something we've been working on for about 3 years now in various guises. I'm just going to summarize some of the stuff that I presented last year at PTEC very briefly, and then mostly focus on the work we've done in the last year with Bonnie Drozdowski and myself. So, let's just go back to the title for a second. So just to be clear what we're talking about here, this is a project to develop subsoil guidelines for hydrocarbons at Alberta green zone sites. And when I presented the last year's version, Gladys kindly woke me up and said, well, what the heck is the Alberta green zone, please? And I think most practitioners in Alberta would be familiar with it, but I thought I'd start by throwing up a slide talking about where the green zone is. Essentially, it's an administrative criteria in Alberta to indicate primarily the forested parts of the province, which are less inhabited, as opposed to the white zone, which is more agricultural. But why are we doing this? Why are we trying to develop guidelines for the green zone? We don't normally do that. We don't normally have a set of guidelines which are specific to one part of the province or another. But the reason we were looking into this was the fact that the existing Alberta Petroleum Hydrocarbon subsoil guidelines, they're based on the Petroleum Hydrocarbon Canada-wide standard, and they primarily consider urban settings, or a lot of considerations which are relevant to urban settings, which is all fine and good, which is as it should be. However, once we're up in the green zone, and obviously there's a lot of industrial sites that are up in our Alberta green zone, we actually do have quite a different set of considerations up there, and we feel that there may be a different set of subsoil guidelines that could be appropriate for managing green zone sites. The two specific attributes of those guidelines that we were trying to look at, the first one was the depth at which the eco-contact pathway can be excluded, and the second one is what the management limits might be, because what the Alberta Tier 1 guidelines allow you currently to exclude the eco-contact pathway below a 3 metre depth, and once you do that, typically you're left with using the management limits. So we were looking at both those elements. Just to be really clear here, the intended application of these guidelines is that they would be applicable to forested Alberta green zone sites. Specifically on public land, so yes, ESID controlled land. But moreover, they should be, they're really only intended to be applied within the green zone to locations that would be considered remote, i.e. remote from regular human habitation, and at which future subsurface disturbance would be not expected. So, I just want to give a brief recap of the first part of the presentation, which is the rooting zone piece. When we came into this project, there weren't any solid data to say, okay, how deep do trees root anywhere in the province, let alone in the boreal. Really briefly, this was a broad brush summary of a literature study, and showed us that the deepest rooting appropriate species was the lodgepole pine of the species we'd expect in the green zone, and that in fine-grained soils, the maximum rooting depth in the literature for lodgepole was about 1.5 meters. So that was a summary of the literature survey. We decided it would be worthwhile to go out and try and validate that. So we went through a program of digging a bunch of holes essentially throughout the green zone adjacent to mature trees, and making observations and measurements of the rooting density, but in particular the maximum rooting depth. We kind of basically pick whichever species were the largest, most mature trees in the locations we were working at. We were trying to get access to locations all through the green zone, and we got a reasonable good distribution there, a total of 16 sites that we were able to access over spring and summer of 2012. The data out of that field validation actually was quite similar to the literature survey. Again, we're exclusively looking at fine-grained soil sites, because that was our focus here. And we found that the deepest that we saw was, again, it was the lodgepole pine. 1.40 meters was the deepest rooting depth that we were able to measure. And so we felt that supported quite nicely the literature value of 1.5 meters. We were careful in selecting these sites to make sure that we were picking sites that didn't have anything that might otherwise be impacting that rooting depth. So we avoided sites with a shallow water table or with a shallow bedrock or anything else that might restrict the rooting depth of these trees. So that was just a very brief recap of what I presented last year on that rooting depth, just to put us back into context. All this was fine-grained soil. What we found for coarse-grained soil, that default value of 3 meters was about right. Some of the coarse-grained, some of the trees, deeper rooting trees in the coarse-grained soil would actually go down to 3 meters. So in summary, we looked at a total of 16 sites. We dug holes next to 44 trees, and we felt that the appropriate values to use for maximum rooting depth were 1.5 meters for fine and 3 meters for coarse. So moving on to the other part of the project, which is the main focus of the talk today, and this is the work that Bonnie and I have been working on. We were trying to look into a little bit more deeply into the management limits. Now, the existing management limits came out of the PHC Canada-wide standard. That was the work that was done in 2000, 2001, and then revised quite substantially in 2007, 2008. These are our values. So for F2, the management limit currently is 1,000 milligrams per kilogram, but that's based on inhalation exposure to a worker installing something in a utility trench. For F3, we've got a range of numbers between 2,500 and 5,000, and in that case, our sort of limiting consideration are these technological factors. Now, to be fair, when we tried to come up with management limits in the discussions around the Canada-wide standard in 2007, the concept came in fairly late in the game, and to be fair, there wasn't a lot of either budget or time to look into a lot of these issues in any great detail. And so inevitably these numbers were based on a fairly limited data set. But the technical steering committee of this project sat down and felt that the considerations that went into the Canada-wide standard management limits weren't necessarily all applicable to the green zone. And so what we did was we looked at all those considerations and said, well, we'll throw out a few considerations like the work of putting something in a utility trench, which just really aren't relevant to a green zone, and we'll also add a few more that we feel may have been missed in the first go round. What we were left with was a list of 4 main considerations that we felt should be used for setting management limits in the green zone, and that is, first one was mobile free phase formation. This turned out to be a lot of the work of the project, also referred to as residual saturation. We'll come back to that in a moment. The other ones were obviously we want to make sure that we're not leaving soils which are a fire or explosion hazard. We looked at hydrophobicity as a valid consideration, because obviously we don't want to be creating hydrophobic soils. And we also considered upward migration, and by that we mean in a situation perhaps where a site had been remediated down to, say, 1.5 meters, and the root zone replaced with clean soil, the concern of whether or not we might have upwards migration of more contaminated subsoils back up into the rooting zone. So this is where Bonnie came in. You see a photo of her hard at work sieving soils there. Essentially, we were trying to determine valid data for the residual saturation of our hydrocarbon fractions. Now, there are methods in the literature, I wouldn't say standard methods, but there are published methods for determining residual saturation. And there is quite a bit of data, there are quite a bit of data out there for the residual saturation of various hydrocarbons. But particularly, mostly that's for existing products like diesel, lube oils, and so on. There are no data that we were able to find, and I'm fairly sure there aren't any, for the actual CCME hydrocarbon fractions. So we put together this experimental design using the published methods initially, and our scope of work was to look at coarse and fine-grained soils. We felt that the starting moisture content of the soil was likely important, so we had what we call dry and wet soils, the wet soils being soils at field capacity. And we focused on F2 and F3 petroleum hydrocarbons for our work. The reason for that was that Alberta Environment had indicated to us that they were open to looking at new data to possibly revise management limits for the green zone, but they felt that the F1 was already where it should be. They weren't interested in seeing that one move, so we dropped that off the list. And F4 we left off the list. It presents a lot of practical problems to dealing with because it's so sticky, basically, so thick. We would need to heat it to work with it. And also F4 rarely drives remediation at site. So we focused our efforts and time on the F2 and F3 fractions. We did this work in 2 phases. We had a first cut, which we thought was our definitive test, but we ended up evolving into the range finding, as practical work often does, in October of last year, using the published methods. And then in December, we came back and said, okay, we can actually think we can improve on these methods and increase our number of reps in a focused sort of way to get a stronger data set. This post-draining water flash I'm going to come back to in a moment. So here's photographs of Bonnie's lab there, just an example here. So essentially, just stepping back a little bit, all of these residual saturation methods, the way they work is that we'll take a soil, we'll saturate it with hydrocarbon or some other product, we'll allow that to drain, and the published methods were saying 7 days. We found in our second iteration that 21 days worked better. But essentially we'll allow the column to drain until nothing more drains out, and then we'll call that the residual saturation. So here you can see our columns of one particular rep saturating from the bottom up with F2, which is conveniently bright red because the lab dyed it for us, so we can actually see it. What we did then was, once the columns were saturated with hydrocarbon, we drained them in the definitive test. We drained them for 21 days, dropped out the sample, and analysed separately the top and the bottom half of the column. Big shout out to Exova here. We had budget enough to analyse each of our samples just once each, having so many replicates of different soils and different hydrocarbon fractions, and Exova kindly upped that to triplicate analysis as a donation in kind. So that really improved the statistics of our data set. So hats off to them. One final thing that we threw into the experimental method was something that we're just referring to here as a post-saturation water flash. What we felt is that in the real world, we've got our free-phase plume in the ground, and that's fine. It drains until it's not moving anymore. But what happens the next spring when the water table rises? Can that possibly remobilize any more free phase from that saturated soil? And so we picked one out of each 6 sets of reps, and after it had drained for 21 days, we flooded it from the bottom with water to see if we could lift off any free phase product. We found for 3 out of our 4 situations we couldn't, but for the F2 columns with coarse grained soil, we were able to mobilize a little bit more residual hydrocarbon. So from that we determined that if we hadn't done this, we would have overestimated what the residual hydrocarbon should have been. And so we used this to correct it downwards a little bit for that particular case. So that was the residual hydrocarbon. That was the lion's share of the work. The rest of this is quite straightforward and quick. Hydrophobicity, we just basically spiked a large series of different concentrations into fine and coarse soil using dry and wet starting points as well, all the way from 0 all the way up to 64,000 with F2 and F3, and then we ran the standard MED or molarity of ethanol droplet test just to see which soils we could make which soils we could make hydrophobic, and we're looking for the threshold below which we see no hydrophobicity. Flammability turned out to be even more straightforward. We started off just basically applying a naked flame to these various concentrations of soil. Couldn't get any of them to burn at all, and in the end we tried putting the flames directly on the F2 and F3 cuts and couldn't even get them to burn. So at that point decided that the flammability wasn't an issue with these particular fractions. Upwards migration, originally we'd anticipated handling this through a modeling approach to see how much hydrocarbon we might expect to move up into the root zone. As it turned out, though, the precursor to the study that Bonnie has just presented had some data that was just perfect for what we wanted. Essentially, it was those columns that Bonnie showed, with contaminated subsoil, clean overburden, if you will, and a 15-month test growing up alfalfa using, and the contamination was jet fuel or crude oil. Because all of the watering, as Bonnie mentioned, all the watering was added from the base. There was no water added to the surface. There was significant upwards migration, of course, as the roots draw that up. And just conveniently in this experiment, based on the analysis that they did at the end, they were able to show that there was significant upwards movement of salt from the subsoil up into the rooting zone, but there was no upward movement of a PHC, which turned out to be exactly what we were looking to try and show. And so we felt that was a strong experimental correlation, a confirmation rather, of the fact that upwards migration from a contaminated subsoil back up into the rooting zone wasn't likely to be a limiting consideration. Just a brief photograph of Andrei Startsev's columns there in 2009. So, tying it all together, what do we feel that leaves us for our recommended green zone management limits? We've got a table here, and we've got our two hydrocarbon types and two soil types up the side, and then these four considerations that we were looking at across the top. So most recently, sort of working from the end of the talk back, upward migration we didn't feel was a consideration or a limiting consideration for any of these situations, nor did we feel that for the flammability based on what we'd measured. Hydrophobicity, it seemed to be a limiting consideration for the F3 in coarse soil, and so that dictated what we felt should be the management limit for F3 in coarse soil. The other three situations, the F3 in fine, and both the F2s, as we somewhat expected, the residual saturation turned out to be the limiting factor there. With just a footnote that in the case of the F2 coarse soil, we had, I think we measured originally 14,000 or something. We scaled that back down to 9 to take account of that additional hydrocarbon that we were able to mobilize when we had the post-saturation water flush. So those are where we're at for our proposed green zone management limits. And I'd just like to tie up by acknowledging our funders. This was a great collaborative project. We had funding from all sorts of places, from 2 different calendar years of PTAC funding. And we also had donations or funding from each of Conoco, Synovus and Husky. And then also we had funding in kind from Millennium, from AITF and from Exova. So I'd like to thank all of those funders